Hi, I'm Ed Statham. I'm the Associate Program Manager for Orbiter Operations with Boeing. I'm here to talk about design tolerances. The key here is to try not to over-design. Two things really drive this in today's world. One is the natural engineering affinity to always replace good with better. They want to drive to the ultimate solution. And second is the key improvements in the tools today allow you to hold greater accuracies than ever before. And the question is, should you, and what are the trades? Complex limited production hardware in many ways is far more likened to prototype hardware than it is normal manufacturing where you would have a larger number of units being produced. This, in essence, drives you to a fleet of however many, but each unique. So you might have a total fleet of three, but three unique vehicles. High precision with tight tolerances has a compounding effect as you step up in level. It starts, of course, with the component level, where there's a tendency to want to overstate the requirements. This then has an additive effect as you go up to the system level and then on up to the vehicle level. And the compounding effect is whatever you struggled with at the low level and you had tight tolerances, as you step up, you become further and further away from being able to achieve a fit and meet the requirements. One of my more interesting stories involving new tools, at least interesting to me, is we had a large test fixture that we had to fabricate out in the laboratory, and the individual designer laid it out in CATIA. He then came by for a visit to see how we were progressing in assembling the test fixture and was shocked and horrified to discover that we were trimming the large I-beams in place. After discussing the reasons why, we took him into the design center and showed him that the absolutely flat surface he had designed to in CATIA was not represented in the laboratory floor. So he'd over-specified. He had used absolute surfaces, which of course don't exist. So it was better to allow trim to fit holding critical interfaces than to try to exactly machine the parts or fabricate the parts to exact dimensions. Instrumentation accuracy is another area that caused a lot of consternation in the shuttle program. You tend to have engineers that want to hold very tight tolerances across a relatively large allowable. If you wanted to control a measurement, you want the tolerance to be 230 degrees plus or minus a degree. You have an accuracy requirement of some type on the instrument that's actually doing the measurement. That could be, say, 10 to 1. So now I've got to be able to measure to 1/10 of a degree in order to validate that I'm within the 1 degree requirement. It's over-specifying. And a lot of times what you find is that when you match up the requirement for instrumentation accuracy against the design requirement, you find that you don't have instrumentation that will actually achieve those results. So you end up having to take a waiver on your instrumentation accuracy. A way to avoid that is simply opening up the tolerance. Hi, I'm Ed Statham. I'm the Associate Program Manager for Orbiter Operations with Boeing. In design considerations, you should really try to simplify and in essence create the most robust design possible. This has considerable advantage in cost and schedule risk. The simpler, the more interchangeable the parts, the better. You want to try to define tolerances that are appropriate and offer the maximum flexibility. Precision should really only be controlled at critical interfaces. If you have 5 sides to a given component and only 2 are required to be controlled, then only in exact the tight controls on those two surfaces, let the other two have somewhat lower tolerance. Consider to the greatest extent possible trim to fit or things like match drilling. Treat it like a prototype. It will give you a higher assurance of fit up when you get to final assembly. You really want to go look at your concept of operation, see what the real requirements are, what's the uncertainty in the environment, and then try to tailor your tolerances to what you're most likely to see that allows you to achieve the given performance. It is true engineering to be able to start conceptually and keep in mind what the ultimate goal is and not overspecify. Producing more robust designs without excessively tight tolerances allows future NASA programs to develop less complex design, lower cost systems, and reduce both cost and schedule risk as you go through the development cycle. Hi, I'm Ed Statham. I'm the Associate Program Manager for Orbiter Operations with Boeing. I was truly raised by a man that believed that if you could not explain a design on the back of an envelope, now he would go all the way up to a legal size envelope if pushed, but if you couldn't explain the design and how it met the parameters in a relatively small, simple way, it was deemed to be too complex to implement. I still think that's worthy of consideration. Today, we all too often jump into the tool that has extraordinary capabilities compared to what they had, say, during Apollo, and we tend to let what the tool can do dictate what we do. We've lost the art of defining overall performance objectives and being able to tell whether we are in the ballpark or not. We let the equipment tell us whether we're there or not, instead of knowing from some rough analysis what the right area is. I was raised by a guy with a slide rule, and actually I had a post-Versalog. So there was a lot to be said from a production and implementation standpoint. It forced you to designs that were more robust because you didn't have the high accuracy. So you designed trying to take into account the unknowns and the things that could change.